Click the bell icon to get latest videos from Ekeeda.
Hello friends, we have seen two examples of how to solve homogeneous linear partial differential equation with constant coefficients. In this video, we will be seeing two more examples of the same type. Let us take the third example of homogeneous linear partial differential equations with constant coefficient. Our example is del square z by del x square plus 3 del square z by del x del y plus 2 del square z by del y square is equal to 12xy. Let us first convert the left hand side as a function of d and d dash, where d is partial differential by x and d dash is partial derivative with respect to y. We'll substitute this. What do we get on the left hand side? So this is our partial differential equation in terms of d and d dash. Comparing with in the standard form, we will be getting function of d d dash as and the function of x and y as. Now we have got f of d d dash and a function of x and y. Let us proceed to find out the CF and the PI. To find the CF, that is the complementary function, first we find the auxiliary equation. We substitute d is equal to m and d dash is equal to 1 in the function of d d dash and equate it to 0. Now we will solve this equation. Solving this equation, we get our roots, that is the values of m as so we have got the values of m1 as minus 2 and m2 as minus 1. Therefore, our complementary function will be is f1y minus 2x plus f2y minus 1x. Y minus 1x is y minus x. So this is our first part of the solution, which is the complementary function. Let us go ahead and find out the particular integral, that is the PI. For finding PI, let us rewrite the function of x comma y. This function is in the form of x raised to m into y raised to n, where we have x raised to 1 and y raised to 1. So m is 1 and n is also 1. Let us also see what is the function of d d dash. Now we can express this particular function as product of linear factors. Thus, we have factorized the function of d d dash as d plus 2d dash into d plus d dash. Now, applying the condition when the function of d d dash can be factorized into linear factors, we will be finding the particular integral for this particular question. Now, let us see what was the condition. What was that particular case to find the PI? When we could express f of d d dash as d minus md dash, then PI was found out by We used to find out pi by integrating the function f of xy by substituting y is equal to c minus mx. So in the function of f of xy, we will substitute y is equal to c minus mx, where m is nothing but the part of the linear factor d minus md dash. Correct? Now comparing this with our equation, with our linear factors, we have two linear factors, d plus 2d dash, d plus d dash. We will be considering each factor one at a time. So let us consider the d plus d dash factor first. We will write our pi as apply this linear factor using the above condition. Comparing c minus mx, or rather d minus md dash with d plus d dash, we will have m is equal to minus 1. Hence, we have substituted m is equal to minus 1 in this. C minus minus 1, that is c plus 1 x, that is c plus x. So, instead of y, we will put c plus x. Our function was 12xy. So, instead of y, put c plus x. So, 12x into c plus x. Integral of 12x into c plus x of dx. Open the bracket and let us integrate. So what do we get on integrating? Let us simplify and write this. And now we had substituted y is equal to c plus x. So c will be equal to y minus x. Simplifying this further, we will be getting so this is after applying the first linear factor. This is our second linear factor. Comparing it with we have, therefore, we will be putting y is equal to c minus mx. Let us see how to find the pi using y is equal to c plus 2x when m was equal to minus 2. We have substituted y is equal to c plus 2x in our question. The last form of the equation that we had got was the expression 6x square y square minus 2x cube. So 6x square y square minus 2x cube and the integral of the entire thing. Let us first simplify and then integrate. Simplifying this further, we get this is after applying the first linear factor. Now we will be applying the second linear factor, which is d plus 2d dash. So let us compare this with d minus d md dash. We get m as equal to minus 2. Therefore, y will be equal to c minus mx, which is therefore equal to, so we have to substitute y is equal to c plus 2x in f of xy. Our f of xy is the last function of x and y, the last expression of x and y, which was 6x square y minus 2x cube. So instead of y, we put c plus 2x. And we integrate it with respect to x. Let us integrate this and find out the particular integral. Let us first simplify the expression that we have derived and then integrate. This is a simplified expression integrating both the terms. Now, let us see if we can simplify this and get our final answer. This is our final PI. However, we still have a constant c in this. We had substituted y is equal to c plus 2x. So, c will be equal to y minus 2x. So, what do we get after simplifying this further? That's our particular integral, which is the second part of the solution. Now let us combine the two parts to find the final solution. Let us move to the next example of homogeneous linear partial differential equation with constant coefficient. The next example is r minus s minus 2t is equal to y minus 1 into e raised to x. Now here we need to understand what do you mean by r, s and t. The standard definitions of r, s and t are: r is equal to del square z by del x square, s is equal to del square z by del x del y, and t is equal to del square z by del y square. So substituting these three values in the given question, we get again substituting del by del x as d and del by del y as d dash. Comparing this with our standard form of homogeneous linear partial differential equation, we get thus f of d dash is d square minus d dash minus 2d dash square, and f of xy is y minus 1 whole into e raised to x. Let us find the CF and PI and hence find the complete solution. For finding CF, first we find the auxiliary equation by substituting d is equal to m and d dash is equal to 1. Therefore, we get f of m comma 1 and we equate it to 0. On solving this equation, we get the roots of m. We got the roots as m1 is 2 and m2 is minus 1. Therefore, our complementary function is f1 into y plus m1x, that is y plus 2x, and plus f2 into y plus m2x. Our m2 is minus 1, so we have f2 of y minus x. This is the first part of our complete solution, that is complementary function. Let us find the particular integral. In this case, what is our function of x comma y? Y minus 1 into e raised to x. At the same time, our function of d comma d dash is we can factorize this and into linear factors. Thus, we have factorized the given function of d comma d dash into d minus 2d dash and d plus d dash. So, we can use the rule of particular integral when f dd dash is converted into linear factors. The rule is thus if we have function of dd dash as linear factor d minus md dash, then our rule was we would integrate the function x comma y by substituting y is equal to c minus mx. So instead of y we put c minus mx, where m is the same as d minus md dash. Let us compare our linear factors with d minus md dash, get the value of m, get the function f of xy where y is c minus x, and then integrate it further. What are our linear factors? So our linear factors are d minus 2d dash and d plus d dash. First we will consider the part d plus d dash. We have, and thus y will be equal to c minus mx. We have substituted m is equal to minus 1. So minus of minus 1 is plus 1. So c plus x. Now we integrate. We have to integrate the function f x minus c minus mx, which is equal to f of x comma c plus x. So instead of y we put c plus x, but our function was y minus 1 into e raised to x. So we have got our function. Let us integrate now and find the particular integral. We will be applying the second factor. So first factor we will be writing as it is in the denominator. Let us first write both the factors and then apply the rule. Applying the rule to the first factor, we have let us integrate this and then in the next round apply the rule for the second factor. Let us first expand and check how to integrate it. So, while integrating it, the first part will give the answer c into e raised to x. C is constant, e raised to x integral is e raised to x. The last part also, that is minus e raised to x, will also give us the integration as e raised to x. However, the second term, x into e raised to x, we will be integrating by parts and we will get x minus 1 into e raised to x. Let us write the answer. This is the final answer after integration. Simplifying this and resubstituting the value of c, now we had substituted y is equal to c plus x. Therefore, we will be resubstituting c is equal to y minus x. Thus, after simplifying and applying the first linear factor, we get Again, comparing the second linear factor d minus 2d dash with d minus md dash, getting the value of m and applying the same rule for the particular integral. Thus, in this case, we get the value of y as c minus mx, m is equal to 2, so c minus 2x. We substitute this value of y in this particular part of the expression and we integrate it with respect to x. But y was equal to c minus 2x. Multiply e raised to x with each term to see what are the integrals. The first term c into e raised to x, c is constant, the integral of e raised to x is e raised to x. The last term minus 2 into e raised to x, minus 2 is a constant, e raised to x integral is e raised to x. We will have to worry about the middle term, which is integration by parts. Again, the answer of x into e raised to x is x minus 1 into e raised to x. Let us write the answers of all the three terms, that is the integrals of all the three terms. Therefore, we get our pi as the last two terms gets cancelled. Also, we resubstitute c is equal to y plus 2x. The last two terms got cancelled. Open the bracket here. These terms also will get cancelled and therefore our final answer for particular integral will be this was the second part of the solution. Let us write both the parts and write our final solution for the given homogeneous linear partial differential equation. Therefore, the final solution is CF plus PI. The part of CF plus the part of CI, which is this is the final solution for the given homogeneous linear partial differential equation. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.